Thank you for your kind introduction, and thank you for permitting your inconvenience. Well, let me start. Here is the content of my talk. Predicting accurate temperature dependence of the fracture toughness of a material in the ductile to brittle transition temperature region, denoted as JC, is very important in structural integrity assessment, considering the large scatter and the test specimen size effect of JC. Predicting accurate temperature dependence from little test data has been of interest to engineers and researchers. One of the widely accepted methods to predict temperature dependence of the cleavage fracture toughness is the master curve approach. The approach assumes the statistical weakest link model for cleavage fracture and uses Weibull distribution to express the scatter of fracture toughness KJC. The procedure is based on a concept that the normalized curve of a median fracture toughness in terms of KJC for 1T specimen, 25 millimeter size specimen, versus temperatures is applicable to a wide range of ferritic pressure vessel and structural steels. Besides the efforts to apply the method, the approach is not without its limitations. For example, some recent studies have reported that the Weibull parameters vary with test specimen size and temperature, and different from those stated in the master curve approach, and thus the KJC temperature dependence. We first thought to re-examine Chen et al.'s opinion that it is necessary to distinguish the concept of the minimum fracture toughness or the lower boundary value of toughness from that of the scatter band of toughness. The former is a definite parameter determined by the specimen geometry and yielding properties, and the latter is a statistical behavior determined by the distribution of the weakest constituent. We interpreted Chen et al.'s opinion as meaning that, at least, the lower bound fracture toughness can be predicted by running an elastic plastic finite element analysis, EPFEA, with a given stress-strain relationship and a failure criterion. For the failure criterion, we considered one of the modified Ritchie-Rice failure criterion, that is, the 4 times CTOD sigma 2 to C criterion, which predicts the onset of cleavage fracture when the crack opening stress sigma 2 to measured at the distance from the crack tip equal to 4 times CTOD, a crack tip opening displacement delta T, hereafter denoted as sigma 2 to D, exceeds a critical value sigma 2 to C. This criterion was validated as explaining the crack tips dependence of JC by Dodds et al. And the test specimen thickness effect of JC by us through the examination of the applicability of the 4 times CTOD sigma 2 to C criterion to the decommissioned reactor pressure vessel steel database, a JC database with specimen thicknesses ranging from 8 to 254 millimeter. We realized that the convergence of sigma 2 to D for increasing load is necessary for fracture initiation because the critical value sigma 2 to C is the converged value of sigma 2 to D. Considering the fact that fracture always occurred after sigma 2 to D reached sigma 2 to C, we thought that the minimum J that could satisfy sigma 2 to D is equal to sigma 2 to C must correspond to the lower bound fracture toughness for the specimen and the material considered. This minimum J can be definitely obtained from EPFEA, which is consistent with Chen et al.'s opinion that the lower bound JC is a definite parameter determined by the specimen geometry and yielding properties. Given these observations, we thought that the temperature dependency of the lower bound fracture toughness might be predicted by the merging of the minimum J that could satisfy sigma 2 to D is equal to sigma 2 to C by calculating EPFEA with a stress-strain relationships for the corresponding temperatures. Thus, the objective of this work was set to predict and validate the temperature dependence of the lower bound JC by the proposed method. Given that the room temperature tensile to yield stress ratio of the Euro RPBs and Japanese RPBs is 1.3, 0.55% carbon steel GIS S55C, whose room temperature stress ratio is known to show a higher value of 1.8, was selected for examination. From the Sharpie impact test results, test temperature was selected as minus 25 and 20 centigrade. The tensile properties for these temperatures are shown in these figures. A rectangular cross-section SED specimen of width 25 mm was examined. Details of the EPFEA are summarized on this page. FEAJ, designated as JFEA, was evaluated by using the load versus crack mouth opening displacement diagram based on ASTM E1921. CTOD was measured at this node A. After confirming that the linear portion of the load versus low line displacement diagram showed good agreement with those described in ASTM E1820, the relationship between sigma 2 to D, the crack opening stress sigma 2 to measured at the distance from the crack would be equal to 4 times CTOD at the specimen midplane, and JFEA was summarized in these figures. For both temperatures, the converging tendency for increasing JFEA was observed for both temperatures. Considering the fact that fracture always initiated after sigma 2 to D reached sigma 2 to C, we thought that the minimum J that could satisfy sigma 2 to D is equal to sigma 2 to C, hereafter denoted as JS, would give a prediction of the lower bound fracture toughness for the specific specimen at the specified temperature. Considering the fact that there is not a definite method to determine the converged value of sigma 2 to D, here we applied the following method. First, the data set of sigma 2 to D and JFEA was fitted with a function shown here. Then, the J at the value of normalized sigma 2 to D over the converged value of alpha 1 plus alpha 2 is equal to 0.95 was defined as JS, the predicted lower bound fracture toughness. By using this method, the values of JS was obtained as 5.5 and 9.3 Newton per millimeter for these temperatures respectively. The tendency that JES increases with increasing temperature was observed as expected. Fracture toughness tests were conducted in accordance with ASTM E1921. The mass curve reference temperature T0 for 1T specimen was obtained as 30.6 centigrade obtained from the results at minus 25 centigrade. Then, the mass curve for half T specimen, that is KJC half T, together with a 2% and 98% tolerance bound curves were obtained as shown in this figure. We see from this figure that the predicted KJSs were sufficiently conservative compared with the experimental results and close to the 2% tolerance bound values. Though there might be an opinion that 2% tolerance bound values are still not the lower bound values in a strict sense, it seems that the predicted KJSs gives a good estimate of the lower bound KJC in a practical sense. Thus, we concluded that the proposed framework has a possibility to transfer the lower bound JC between different temperatures in an engineering sense. The success in the current work indicates that the lower bound JC for a given specimen and temperature can be predicted with one experimental data. That is, a stress-strain relationship. If so, the lower bound JCs might be transferred between different specimen types and thicknesses. And this result will be presented in another work at this conference. Despite the presented success, we acknowledge some needs of some future works to be done before finalizing the proposed framework. We are aware that the threshold value of 0.95 or FE modeling may affect the predicted JSs, and thus working on a way to standardize this issue. Besides this numerical procedure, we are also aware that we have to clarify the physical meaning of the predicted JSs, though this is an engineering framework. Some rough side evidence we recognize is that the predicted JS for 1TCT specimen at mass curve reference temperature T0 seem to correspond to the turning point of the load versus low line displacement diagram. That is, if fracture is to occur at this load, then no plastic deformation is observed before cleavage fracture. Because we are considering elastic plastic fracture toughness JC, this finding seems to give some idea of the lower bound fracture toughness. The success of the mass curve approach based on 1T specimen seemed to support our finding. Here is the conclusions of my talk. Thank you for your close attention.